Welcome to part 3 of section 2.4. Here we will find how to find the equations of the tangent line and the normal line. These are referred to as just the tangent and the normal. I'm not sure why in calculus we don't use the word line sometimes after these words, but that's fine. But they are both lines. So these are just 3 pieces of information that you need to recall from just this past week and from well before that as well. So the first piece of information that you need to recall is what a tangent line is. A tangent line, as shown here, is a line that touches the curve being our function, only one time. It touches at one point and one point only, and its slope is identified as, or abbreviated as, m for slope sub tan, to represent that it's the slope of this tangent line. The second thing that we need to recall from earlier is that slopes of perpendicular lines are opposite reciprocals. Remember, perpendicular means that two lines intersect and form a 90-degree angle, and the symbol for perpendicular is an upside down T. And then an example of an opposite reciprocal would be like the number 2, and then opposite means it would be opposite, so negative, and then reciprocal means flip. So an example of opposite reciprocals is 2 and negative 1/2. The last piece of information that you need to recall from your pre-calculus times is the point slope form for finding the equation of a line. And we're obviously going to need this because we are finding equations of the tangent line, and we'll find out what a normal line is. The point slope form is best used when you obviously have a point and a slope. So m is the slope, x sub 1, y sub 1 is the point that we have. So this is the point slope form for finding the equation of anything linear. So if you recall those 3 pieces of information, then you should be good today, because I'm not going to really go over these types of ideas. If you do need help with finding the equation of a line, I suggest you look back at our earlier videos for the prerequisites of calculus. We did this a little bit, or just find another video online, or you can ask me at my office hours for these pre-calculus ideas. Let's take a look at the function x squared here in red. Nothing too crazy about it, just a parabola. And I want to focus on the coordinate point when x is 2, so that coordinate point would be 2, 4. And then the tangent line there, I've already found, which we'll learn how to do today, is 4x minus 4. And so the tangent line hits at that one point, 2, 4. Because it's so hard to see so close to some things, it does look like this line and the parabola kind of are mushed up against each other for a long time, but they're really not. They're only hitting at one point. And then finally, the normal line is perpendicular to the tangent line. So we'll notice here that the blue tangent line and the green normal line are perpendicular. Note that their slopes, 4 and negative 1/4, are opposite reciprocals of one another, and they intersect at that same coordinate point. So the tangent line and the normal line do hit our parabola at this one spot. The normal line does happen to hit the parabola again over here if we went to the left. So the tangent line is going to lie tangent, touching only once, and the normal line intersects the tangent line and is perpendicular to it. So we've established the fact that the normal line and the tangent lines to a curve are perpendicular. They will both hit our curve at the same spot, the spot in question. Let's take a look at our first example, f of x equals x squared. The first thing we do is we want to find the slope of the curve, and I forgot to put a coordinate point here. Let's find the slope of this curve, y equals x squared, at the coordinate point we just talked about, x equals 2. At the end of this example, we'll take a look back at our Desmos screen and ensure that everything looks good. So we want to really delve into this example. So we have our regular old parabola. I kept it simple for our first example, just x squared. So to find the slope of the curve at x equals 2, we use our limit that we found in the last 2 videos. So in order to find the slope of the curve at exactly x equals 2, we want to find m sub tan at x equals 2. So we're going to find the limit as h approaches 0 of f of 2 plus h minus f of 2 all over h. All right, so that is the limit as h goes to 0. And then I'm going to plug 2 plus h in. So we'll do 2 plus h squared minus f of 2. F of 2 is 2 squared. Still all over h. Now I do want to point out, right, if we use direct substitution here, we'd get 2 plus 0, so 2 squared minus 2 squared over 0. So we'd have 0 over 0, indeterminate form. We have to keep going. So we're going to expand the 2 plus h squared. That is a limit right there, limit, oops. And then when we square 2 plus h, we'll do 2 plus h times 2 plus h. So we'll get 4 plus 4h plus h squared minus 4. The way that I do that quickly in my head, I can't remember if I've shared this with you, is I square the first, square the last. I do that first and last. To find this middle piece, you multiply these two by each other, 2 times h, 2h, and double it. So I do this squared, multiply them together, double it, then the last piece squared. And that's how you can do that quickly in your head. All right, minus 4. Cool, so the 4 and the minus 4 cancel. So in our numerator, we can factor out an h. Our goal for doing that is because we want the h's to cancel. So we no longer have 0 over 0. So we're left with 4 plus h. There we go. All over h. These h's can now cancel. Now we can successfully use direct substitution. So when we plug 0 in for h, we'll just be left with 4. So that means our slope of the tangent at x equals 2, m sub tan, is 4. All right, so here's what we've established so far. So I erased all that work, so we made some more room. We found that it is 4. All right, the next thing that we want to find is the equation of the tangent or tangent line at x equals 2, our point in question. Now recall from the recall information at the beginning of the video, we can use point slope form. Now what do we need when we're using point slope form? We need point and slope, exactly what it tells us. So in order to find the equation of any line, tangent or normal, we need a point and a slope. And so far, out of our point, we only have the x-coordinate is 2. We have the slope of the tangent line. We found what the slope of the curve is. The slope of the tangent at x is 2. It's 4. So here's what we're missing. We're missing the y-coordinate when x is 2. Well, if you have a function and you know the x-coordinate, how can you find the y-coordinate? You plug it in. So in order to find the y-coordinate here, I have to plug in 2 into my function. I need to find f of 2. This is f of 2. I'm not going to leave f of 2 there, but how do we find f of 2? We plug 2 in. So 2 squared is 4. So our slope of our tangent and our y-coordinate happen to both be 4 here. That's totally fine. So I'm going to write in 4 there instead of f of 2. Great, now I have all the information needed to use point slope form to find the equation of the tangent line. So here's point slope form. And I'm going to plug in y1, m, and x1, multiply it through, and add 4. Awesome, so this is the equation of our tangent line. The last thing that we're going to find is the equation of our normal. All right, once again, we're asked to find the equation of a line. So we need a point. The point stays the same, it's 2, 4. And we need the slope, m sub nor, the slope of the normal line. Well, we know that the tangent line and the normal line are perpendicular to one another. Therefore, their slopes are opposite reciprocals. The opposite reciprocal of 4 is negative 1/4. So the slope of our normal line is negative 1/4. Once again, we're going to use point slope form. So y minus 4 equals negative 1/4 x minus 2. When we multiply the negative 1/4 through, we'll have negative 1/4 x plus 1/2. Then we add 4 to both sides, which is adding 8/2, so we'll be left with 9/2 over here. And this is the equation of our normal line. Now I wrote that in decimal notation on Desmos because I think decimals are easier to input. So I inputted it in Desmos as negative 0.25x plus 4.5. So here's just a quick look back at our Desmos screen. We have our original parabola in red, x squared. Here's the coordinate point 2, 4. Our tangent line 4x minus 4 hits at that one point and represents how the parabola is changing, the instantaneous rate of change exactly there, which is 4 over 1. And then our normal line is perpendicular to the tangent line, and we can see it does create a 90-degree angle there. Their slopes are in fact negative reciprocals, and it does hit the y-axis at 4.5, so we did find that correctly. Here in our second example, we once again want to find the slope of the curve. This is a little bit more complex of a function, but it's still a parabola. So we want to find the slope of the curve at x equals -2. That means we want to find the slope of the tangent line at x equals -2. So we're going to do the limit as h approaches 0 of f of -2 plus h minus f of -2 all over h. So the limit as h goes to 0, then I need to plug in -2 plus h everywhere there's an x. And we do need to be careful with the squaring and the distributing of negatives here. So that is the f of -2 plus h. Now I'm going to subtract f of -2, and I'm going to use a big parentheses here because I'm subtracting something with more than one term. So I'm plugging in -2 and being very careful with minus signs and parentheses. All right, so the limit as h goes to 0, and I'm going to distribute that 2, so I'll have minus 4h plus 2, oops, I don't know why I put an h there, minus 4 plus 2h, there we go. Then I'm going to subtract this piece squared. So we're going to expand this binomial here using that quick trick. So we're going to square -2, multiply -2 times h and double it, and then square h. Great. Then I want to figure out what one number this nonsense is. So this is 3 minus 4. So this piece is -1 here. Then we're subtracting a number. That number that we're subtracting is 4, since it's -2 times -2. All right, so that gives us a minus, and then inside those parentheses was a -5. So again, being very careful with subtraction and negatives. Okay, I'm going to combine the 3 minus 4 in that line. And I'm going to combine that and get a -1. And then this is plus 5 here. So I'm going to combine that. We'll get a -1 plus 5, so that's a 4 altogether. So it was this and this. Then I will put the plus 2h and distribute the minus sign through. So minus 4 plus 4h minus h squared all over h. The 4 minus 4 cancel, and we're left with the limit as h goes to 0 of 6h minus h squared all over h. We can, if we direct substitute, we'll still have the indeterminate form 0 over 0 at this point, so we need to factor out an h. So we're left with 6 minus h all over h. The h's cancel. Then we can plug in 0 for h. We can use direct substitution, and we'll get 6. So the slope of the tangent line at x equals -2 is 6. All right, that allows us to find the equation of our tangent line at x equals -2. All right, in order to find the equation of the tangent or tangent line at x equals -2, we need a point and a slope, m sub tan at that point. We already found the slope of the tangent line at that point, which is 6. We found that in part A. Now we know -2 is the x-coordinate because we're told that, but we do need to find the y-coordinate. In order to find the y-coordinate, if you're given the x-coordinate and a function, is we just plug in -2 into our function. And we actually already did that. We plugged in, we found f of -2 already, and we found that it was -5, but I'm just going to do it again real quick over here, just to show you. So we have 3 plus 2 times -2 minus -2 quantity squared and we'll have 3 minus 4 minus 4. So that gives us -1 minus 4, or -5. Now that we have our point and our slope, we can use point-slope form. So it's y minus -5 or y plus 5 equals 6 times the quantity x minus -2, which is x plus 2. So we'll distribute the 6 through, and we'll get 6x plus 12. Then we'll subtract 5 from each side to get y by itself. So we'll be left with y equals 6x plus 7. The next thing that we want to find is the equation of the normal, or the normal line at x equals -2. Remember that tangent lines and normal lines are perpendicular, so our slope of the normal line is going to be the opposite reciprocal of the slope of the tangent line, and in that case the opposite reciprocal of 6 is -1/6, and we're at the same point, which is -2, -5. We already found that coordinate. Well, we found the y coordinate. So we're going to use point-slope form, so we'll have y plus 5 equals -1/6 x plus 2. Then when we distribute that -1/6, we'll have -1/6 x minus 2 over 6, which is 1/3. Then we'll subtract 5, and 5 is really 15/3. So we have y equals -1/6 x minus 16/3. So I entered these into Desmos, and we can take a look at the red parabola is obviously our original function. The blue is the tangent line. Here's the point -2, -5, where they're all intersecting. And we can see that the blue tangent and the green normal are in fact perpendicular lines. And the blue tangent is representing the slope of our parabola, the slope of our function at exactly when x is -2. It's how our function's changing then, which is very rapidly an increase of 6. A very interesting idea in calculus is when our tangent line is horizontal. Let's think about what that means. A horizontal line has a slope of 0. So we're looking for when is the slope of the tangent 0. We're not told an x-coordinate here. We need to find the x-coordinate so that the m sub tan equals 0. This is important because if you think about a function, if you think about a parabola, in this case what we have is a downward facing parabola, we have a horizontal tangent up at the vertex, at the maximum. At that point, it's sort of like when you're at the top of a hill on a roller coaster, you're like kind of in free fall. Not the first hill, but like once you're already moving real fast and you go up really fast and then you're sort of like kind of like jump out of your seat almost. You're not increasing or decreasing right there. You're like in limbo. And so at the very top there, that is when our tangent line is going to have a slope of 0. It's going to be horizontal. So if you are asked to find when the tangent line's horizontal, you need to find the slope generically and then set it equal to 0. Let's do this example. Instead of finding the slope of the curve at x equals a number, we want to find the slope at x equals a, and then we want to find what is that a. Okay, so let's find the slope of the curve at x equals a. So we're going to do the limit. Let me make this smaller real quick. We want to do the limit as h goes to 0 of f of, not a number, a plus h minus the f of a all over h. This was the generic definition of how to find the slope of any tangent line, the slope of the curve at any point. All right, we can plug in a plus h into our function. If we plug in a plus h, we'll have 3 plus 2 times a plus h minus a plus h quantity squared. So that was f of a plus h. Now I'm going to find f of a and subtract it, of course, in parentheses, since it's more than one term. Okay, so that's what I have. Then we need to do a bunch of algebra here. So calculus is mainly algebra with a few extra ideas thrown in. So I'll have 3 plus 2a plus 2h minus, I'm going to square this using our shortcut, a squared plus 2ah plus h squared, then minus 3 minus 2a plus a squared, all over h. And I want to see, is there anything that I can just cancel out at this point that makes life easier? It looks like we have a positive 3 and a minus 3 and a plus 2a and a minus 2a. So I'm going to keep going from this point. The limit as h goes to 0, we have 2h minus a squared minus 2ah minus h squared, and then plus a squared. Great, so the minus a squared and plus a squared cancel, and I forgot is all over h. There we go. So we have the limit as h goes to 0 of 2h minus 2ah minus h squared all over h. And of course, we can factor out an h here, since if we direct substitute, it's still 0 over 0 at this point. So if we factor an h out of the numerator, we have 2 minus 2a minus h all over h. The h's cancel. When we direct substitute in 0 for h now, we're left with 2 minus 2a. That means that generically or generally, in order to find the slope of the tangent line for any point a on this curve, it's just 2 minus 2a. So did I need to use a? No, I could have used x here. I like just using a different point and just pointing this out. So I'm looking for what is a for this special tangent line when it's horizontal. And a horizontal line, recall, is when the slope is 0. So we need to take this general slope and set it to 0. When we do that, I'll add 2a to both sides and divide by 2. So when a, aka x, since a is just a general x value, when x is 1, our tangent there is horizontal. Let's check it out on Desmos and make sure. All right, looking at Desmos, we can see that our maximum occurs when x is 1. And if we were to draw any tangent lines on here, which I'll draw some in blue, like if we were to draw the tangent line when x is 0, it has a positive slope. If we were to draw the tangent line when x is 2, it has a negative slope. Oops, I should have hit the point there. But if we were to draw a tangent line when x is 1, it's a horizontal tangent line. It has a slope of 0. So x equals 1 was when the tangent line is horizontal, aka when its slope is 0.